And final speaker of the first session of the morning, Sakura Schafer-Nameki, is going to tell us about holography, one-form symmetries, and confinement. So please, Sakura, all yours.
Okay, thanks very much, Wally. And thanks to the other organizers too for setting up this great meeting and for inviting me to speak here. I hope my internet connection is gonna stay stable. Let's fingers crossed. Okay, so I'll report on some work that appeared in April this year with fantastic collaborators, Fabio Pruzzi, most of you know him, and two students, Marika and Dawi, in this paper. And we are totally switching gear. There's no swampland. So if you're a swampland person, this is something different. So the motivation is, well, we've all heard at some point about higher form symmetries. And by now in quantum field theories, they're really well established. So one question you can ask is how, in fact, we can make use of them in string theory, and maybe more interestingly, what is the point of realizing them in string theory? And this sort of class of questions will also be discussed in the session later today. One good answer to this question is, well, string theory allows you to access regimes that you normally can't access easily, something like strong coupling, non-Lagrangian theories. And examples of that are 5D SCFTs and 6D SCFTs that are intrinsically strongly coupled, non-Lagrangian theories like class S theories and related things. And then, of course, the thing that keeps on giving, holography. So strong coupling via holography. And indeed, in the past years, there's been a lot of activity in terms of applying higher form symmetries, studying their implications in that context of these three sort of applications. Okay, so some of you might at this point think, oh, I'm having a deja vu to 2 weeks ago at strings. She was telling me exactly the same thing. Good news is I'm not going to actually focus on this part here, but actually on the final part here, which is sort of the application to holography and how confinement can actually be elucidated in that context, and how higher form symmetries are actually very powerful point of view if incorporated into the setup. So what's the paradigm that I'd like to sort of discuss? It's something you all know very well. We look at 4-dimensional n=1 superangles that has a one-form symmetry, and the one-form symmetry is really a diagnostic for confinement. So if the Wilson lines have area law in a vacuum, the one-form symmetry is unbroken and the theory is confining. Likewise, if it has perimeter law, then the one-form symmetry is spontaneously broken and we're in a deconfining phase. And so what the goal of this talk is really is to focus on the holographic realization of that. And Angel mentioned it in his talk, the Klebanov-Schussler solution, which sort of conjectured that holography could help us understand this IR effect. And what we'd like to sort of point out is that once you put higher form symmetries into the game, we can sharpen sort of the predictions from this holographic duality. Okay, so the plan is I'll start looking at general things like line operators, polarizations, one-form symmetries, just to set sort of the scene. Then I'll discuss how actually in holography, higher form symmetries are realized. And then the final application, which is really where the physics is, we'll look at this holographic setting. And the key sort of ingredient is the supergravity, because it's holography, but the supergravity sort of gives us things like mixed Hopf anomalies and also predicts the IRT QFT that sort of governs the confining phase of superangles. Okay, so let's focus on a pure gauge theory in 4 dimensions. We have a gauge algebra. We simply connect the group G associated to it. Then the set of line operators are the Wilson lines and the Hopf lines. And they're given by the weight lattice, motor root lattice, and the magnetic version. And both of these quotients are just isomorphic to the center of the group G, to simply connect the group G. So if you look at this complete set of lines, and you take 2 of them and insert them in correlators, they're actually not mutually local. And that's because of the Dirac pairing. So actually you pick up phases. And so what this theory is actually not yet a good theory. It's what we'll call relative theory. So to actually get something where you have local line operators, you need to pick a polarization inside L. So lambda is a maximal set of line operators that are mutually local and are sort of, will not have these kind of phase ambiguities. And that's what we then call an absolute theory. So for SUN, the set of lines is just Zn plus Zn, right? The Wilson lines and the 't Hooft lines. And indeed, the Wilson lines and 't Hooft lines have a non-trivial pairing. So a good polarization is, for example, just pick one or the other, right? So W or H. And that's then the global gauge group SUN or PSUN. But there are many other ways you could have picked polarizations. In for SU2, I'll give another example. So the one-form symmetry is then related to a given polarization just by being the Pontryagin dual group. So gamma 1 is just lambda hat, which is Homs from lambda into U1. And if lambda is just a discrete Zn group, that's just Zn again. So in this case, just for SUN, of course, we just have a Zn one-form symmetry. Since we'll be talking about confinement, an interesting sort of question is, are all these lines in this group, are they actually have to have area law? So if we actually have lines that have perimeter law, we should quotient them out. And in a given vacuum, R, the one-form symmetry that's preserved, should then be the quotient of lambda hat modulo the perimeter law lines. And if this quotient is non-trivial, then the theory is confining. Okay, so for SU2, the story is, of course, very well known. We can look at n equals 1, say for SUN. First of all, we expect n vacua. We start with the U1R symmetry, and from field theory, know that the ABJ anomaly breaks this to Z to N. And then chiral symmetry breaking breaks it further to Z2. And then we have sort of N vacua, which are sort of permuted by the remnant Zn group. So for SU2, there are two vacua. One is sort of from the n equals 2s superior point of view, the one where the monopole condenses, and the other one is the one where the dione condenses. And we can now check for each of the polarizations for SU2, what is the one-form symmetry preserved in each of the vacua, so gamma M and gamma D. So there are three polarizations. There's the electric, the magnetic, and the dionic one, which correspond to the gauge group SU2, and then SO3 plus or minus, depending on the theta angle. And then in each of these vacua, we can ask, is the one-form symmetry preserved or not? And for the SU2, of course, both of the vacua are confining, but for SO3 plus, the monopole vacuum is deconfining, and vice versa for H plus W. So this is sort of the field theory story, and we'd like to replicate that from a holographic setting. So one other thing I need to sort of explain is, because we're doing supergravity, this will become important, how we couple, say, theories with certain global symmetries, higher form symmetries to backgrounds, and how we gauge these symmetries. So we have a p-form symmetry, gamma p, the charged objects and general p-dimensional objects, and then the symmetry itself is generated by topological operators, which are codimension p plus 1. So in the one-form symmetry case, in 4 dimensions, we have topological surface operators, and these generate the symmetry. So I can couple the symmetry to a p plus 1 form background field, which takes values in this cohomology, where gamma p is this p-form symmetry group. And then gauging just means sum over all these backgrounds, right? And this is sort of slightly generalizing the standard gauging procedure, because most of the time these gamma p's are just discrete, like Zn groups. So in the simplest case, you can start with the SUN and then gauge the center symmetry and get the PSUN theory, for example. Okay, so this is the basics of the field theory story. I would like to now ask, so what happens if you put this into a holographic setting? So think about your favorite ADS5 times S5 holographic duality in type 2B. We can also generalize it to Sasaki-Einstein, but really the simplest thing is just look at this compactification. We have 5 form flux, and that's dual to 40 n equals 4 superangles with gauge algebra. Let's start with that, SUN. And so one question is, how do you distinguish the different global forms from this bulk perspective? Right, so there should be now different holographic duals depending on what global form the boundary theory has taken. And that actually is something Witten told us a very long time ago already. Consider the type 2B Chern-Simons coupling in 10 dimensions. So we have F5 and B2C2, which are the two forms we have in type 2B for NSMS and RR. And then looking at the fluctuations around a given background, this 85 times 5 background, and denoting these two-form field fluctuations by B2 and C2, then actually there's a 5-dimensional topological coupling, which is just given by B2 wedge C2, DC2 times N. And so this is actually the topological action that will now determine for us what are the global forms of the dual gauge theory. So looking at the EOMs, first of all, they just say that NDB2 and NDC2 are 0. So these are actually two ZN two-form fields that are flat. So we can use them to construct topological surface operators. So if M2 is a surface, I can integrate, exponentiate, and these become then topological surface operators. I'll call them UB and UC. And these actually are mutually not local. So as we exchange them, they pick up a phase, which depends on N, but also on the intersection of these surfaces. So if the surface actually has a boundary, so we have some line gamma, and this line actually is embedded into the boundary of ADS5, then the surface, we can think of it as now a line operator in the field theory. And for this UB case, these are just sort of the operators that will correspond to fundamental strings, and for UC, the D strings. This means then they can end on the boundary, and these will correspond to Wilson lines, and in the C2 case, they correspond to the Toft lines. So a bit more in detail, basically, we look at the boundary conditions for this topological action. For example, put Dirichlet on B2 and Neumann on C2, then the F1 strings can end on the boundary of ADS, and the topological operators UC remain topological surface operators that link with these line operators on the boundary. And so they generate then the one-form symmetry. And you can also turn it around and then get sort of the magnetic version, so the PSUN theory. A nice way to actually see that the resulting one-form symmetry, or that these line operators are really so have a ZN one-form symmetry, is to actually look at sort of the Bianchi identity for the supergravity theory and integrate it over this S5 sphere. So for D7, DF7, the Bianchi is F5 wedge H3. We have 5-form flux, so this is just N times H3. So all this is saying that N F1 strings basically can end on a wrapped D5 brane, and that's just the baryon vertex. So N Wilson line, so to speak, can be screened, and so this has a one-form symmetry as the N. So that's, of course, the simplest possible thing. There are many other boundary conditions, and there's sort of a way to encode them in a version of this action in quite generality. Okay, so that's the so ADS CFT version. We're not interested in that because in a conformal field theory, the one-form symmetry isn't particularly interesting. So the interesting thing really where the one-form symmetry becomes so really important and comes to life is when you're looking at Super-Yang-Mills confining theories. And there's a holographic dual setting, this Klebanov-Starzl solution, which realizes that. So the starting point is, again, something very similar to ADS5 times S5. We start with ADS5 times T11 with 5-form flux. T11 is just the Sasaki-Einstein manifold. If you put the cone over T11, that's the conifold. And so this is just a CFT setting. So the geometry is, roughly speaking, S3 times S2, and then you have a cone over that. So T11 is just topologically S3 times S2. So in addition, if you wrap now on the S2, D5 branes, that induces a 3-form flux on the S3, n units of that. And that actually now means that the S3 can collapse at the tip of the cone. So it stays at finite size. And so what it means is actually we break the conforming variance, and this then produces a non-conformal holographic setting. And the Klebanov-Starzl solution models that sort of along the entire RG group. So very roughly speaking, the solution is now not dual to ADS, but it's dual to some M5, which is just R4, plus the radial direction. And then there's the T11, and that's sort of the solution in the UV. And then it gets slightly modified and extended to the IR. R is the radial coordinate, And we should think of this as really the RG direction for the system. And this function R is written out here. So one interesting thing about the solution is that not only we have no ADS solution, but actually the fluxes also pick up an R dependence. And so only for very specific values of this radial coordinate, which I've written out here, where Rk is the UV scale R0 times e to the k over n, is actually this quantity here an integer. And you really have a dual sort of interpretation in terms of field theory, or you have a sort of integer number of D3 branes. And as you sort of go along this flow, the number of D3s sort of decreases successively. And one question is, okay, what's the dual field theory? Well, that's the famous duality cascade. So in the UV, we start with something like a standard quiver gauge theory, SUN plus m times SUN with bifundamental matter. And as we start the RG flow, then the coupling of this one diverges. We can Seiberg dualize this and get this kind of quiver gauge theory, again with bifundamental matters. We continue the RG flow, this here becomes strongly coupled, and then we Seiberg dualize and get to this, and it continues. And if actually n is a multiple of m, then at the end of this flow, you end up with a pure SUM superyoung-Mills theory. And so we'll assume that's true, so that we end up with just the superyoung-Mills theory. And the conjecture is that the solution is then dual to the confining phase of 4D equals 1 superyoung-Mills. So what's now the expectation, right? So given that that's the conjecture, what actually do we expect putting this now into this one-form symmetry context? So the first thing is the one-form symmetry should be unbroken because it's a confining vacuum. We should see the chiral symmetry breaking, and there's sort of a one-form symmetry way of seeing that in terms of Toft anomaly matching. And the third thing is we would actually like to know what happens in the far IR. Can the supergravity actually tell us what is this gap TQFT that sits in the IR of this cascade? And basically using supergravity techniques, following a lot of this work also by Cassani and Faedo, who did the consistent truncation on T11 to the 5D supergravity, we were able to answer all these 3 points. And that's what I'll discuss in the next couple of minutes. So the first thing is, how do we see the one-form symmetry in the Klebanov-Strassler solution? Again, in the 5D consistent truncation, there is a very similar term to the one I showed you earlier in 8 is 5 times is 5. It's a 5D topological coupling, B2 wedge DC2, where B2 is again the fluctuation of the NS and S2 form, but the C2 is a combination of the 2 form and a component of the 4 form. And this comes with a GCD n, m. So the one-form symmetry I can study now in completely the same way as I did for the 8 is 5 times is 5 case. And this is then just given by GCD n, m. So if n is m, k times m, it's just m. So the boundary conditions, for example, you could impose is that B2 again has Dirichlet. So F1 strings can end and we get Wilson lines, and this is then dual to the SUM theory, the simply connected gauge group case. But you can do this sort of at each one of these slices, R is RK, so you have well-defined integer flux numbers. So the 3-form flux is m, the 5-form flux at that point is n minus k, n minus k times m. And then integrating the Bianchi identities, again, we can see that either you can screen fundamental strings with wrap D5 branes, this coming from this Bianchi, or from these 3 branes on the S3. And overall, so the minimal thing that you actually will screen is a GCD n, m F1 strings. And that's, of course, if you look at the field theory side, this is also in agreement with the one-form symmetry of this quiver. Right? So you have the center symmetries here, but you also have bifundamental matter. Okay, so what about chiral symmetry breaking? So we said there's a U1R symmetry, and that's, of course, in the ADS5 times T11 solution realized in terms of the circle fiber, the read vector in the T11. So T11 is just a circle fibration of a P1 times P1. So we can follow what the supergravity tells us about the background field for this U1R symmetry. The 5D consistent truncation gives us a Strikelberg type coupling, which is given here. A is the background for the U1R symmetry, and G1 is basically DC0, where C0 is an axion. And so this background for the U1R symmetry has a gauge transformation in the supergravity, and that allows us now to actually completely gauge away C0, except for the gauge parameter values given by 2 pi over m to m times z. So the U1 gauge field becomes massive, but there's a remnant which remains there, which is a Z to M zero form symmetry. So from this Strikelberg coupling, we get the breaking of the U1 zero form symmetry to the chiral symmetry Z to M zero. And that's sort of the supergravity version of what the ABJ anomaly does in the field theory. There's also coupling, which is given in terms of in the 5-dimensional supergravity, which is B2, B2A. So B2 is the NS fluctuations, but this also we should think of in terms of the background fields for the one form symmetry. And A was the background for the chiral symmetry, for the zero form symmetry. So this term is really a mixed Toft anomaly between the one form symmetry and the zero form chiral symmetry. So a very nice theorem by Cordova and Omari says, if you have such a topological coupling, then you can only, there exists only a TQ of T that will saturate this anomaly if this is actually integral, this omega. So B2 is in fact really properly sort of written out is the Pontryagin squared of B2. That's even for spin manifolds. And so we have still 1 over m to account for, right? To make this here an integral term. Actually, the only way to do this is that the periods of A are actually multiples of m. So in this way, we see that the Z2M zero form symmetry now needs to also actually break further to Z2. And that's basically chiral symmetry breaking coming from this topological coupling in the supergravity upon sort of just following the logic of that this Toft anomaly needs to be matched with a TQ of T in the IR. Okay. So the third thing is now, can we actually push this further and describe the IR TQ of T that we expect, right? So can the supergravity supply that as well? And the remarkable answer is yes, it can. And so if we look at the supergravity action, so in the IR, the solution actually needs to be sort of extended. It becomes this T star S3 solution because there's this deformed conifold due to this reform flux. There is this topological term, which is given in terms of C0, a C3 field, and again, a coupling B2 squared DC0. And we can evaluate this now in the 4-dimensional boundary. And that gives rise to a TQ of T by identifying this scalar field phi with C0 over M of this form here. And this actually is precisely the 4D TQ of T that is proposed to cancel this anomaly or to match the anomaly as well as to describe the TQ of T of the confining phase of 4D n equals 1 CPMLs. So each of the vacua are labeled by values of phi. So either I phi is just given in terms of the labels L from 0 to n minus 1. And then each of these vacua are separated by domain walls, which in the string theory come from the RAP-D5 branes. And here are basically sourced by e to the I integral over C3. And that actually agrees with, as I said, a prediction just from field theory, where this was sort of argued by pure Toft anomaly matching. Here, the supergravity sort of supplies this theory sort of from the get-go. There's an interesting observation here that something that in supergravity is extremely natural, that these higher form fields have these kinds of gauge transformations that can mix. So B2 has sort of an influence also on the gauge transformation of C3 in terms of interpreting these as backgrounds for one form, and in this case, two form symmetry. It means actually that these two aren't just so product groups, but actually form something called a 3 group, right? So this mixing of the transformations of the background fields means there's a high group structure. And that's also consistent with the fact that this F4 is sort of the gauge invariant field strength for the wrapped D5 frames. Okay, so Roddy, you didn't give me a warning, but I think it's 25, so I have maybe a minute.
Oh, sorry, I did try to give you a warning. I'm not sure you heard me. I spoke
I
up.
think you were muted, but I think I'm on time, so let me just finish
Great,
with conclusions and outlook. So I talked today about confinement for 4D equals 1 superangles and the holographic dual description in terms of the Clapeyron-Strassler solution. That if you look at the citations to Clapeyron-Strassler, you will see that's a huge literature. So what can we add to that? Well, the interesting perspective we're supplying is using one-form symmetry. A lot of the things that you might have observed back then become a lot sharper, right? And we can really pinpoint them, derive them from the supergravity point of view, give them an interpretation in terms of backgrounds, anomalies for these higher form symmetries. And you've seen that the chiral symmetry breaking essentially comes from the supergravity point of view naturally, and perhaps most importantly, we can also access the IRT-QFT. Okay, so some remarks about related setups. As many of you will know, there's also the Maldacena-Nunez solution, that is sort of the S-dual version, where you take wrapped NS5 branes, not D5 branes. And in that context, actually, we can also at least derive the anomaly, this mixed anomaly, this AB squared anomaly, using the anomaly polynomial of the little string from the NS5 brane. Another way to realize 4D equals 1 superanguloses in terms of singular G2 manifolds, so that's more geometric engineering. So the G2 is some C2 mod Zn fibered over S3. The one-form symmetry is very easy to obtain in this context. So there's something observed in this paper with Dave and Brian. The interesting question, the next question is, can you also then see this anomaly and also sort of detect this confinement from looking at this geometric engineering setup? And I think using these sort of methods, looking at these reductions on the links will also be interesting application. We'll have interesting applications and other compactifications. Okay, thanks very much.
Great. Thanks very much, Sakura. And thanks for sticking to the time, even if I didn't speak up loudly enough at 5 minutes. Anyway, so we've got time for some questions. So I have a question, but let me see what else we have for anyone in the audience have a question? So I have a question, Sakura. When you talk about this duality cascade,
yeah.
Where when you have capital N equals K capital M, you get the one form symmetry and this dual. If you had something that was very close to that, like if N and M were very large, but N was equal to Km plus 1, then would you have like a one form symmetry that was just slightly broken?
So N is equal to Km plus 1.
Right,
and
and
still at the end of the cascade, you don't actually get a pure angles, right? So the GCD in this case will be trivial, I think.
So does that come close? I mean, I'm just wondering whether that is very close to N equals Km or whether it's qualitatively a totally different kind of theory.
I think it's qualitatively quite different. But I mean, at least from this point of view, maybe you could say there's sort of you want to probably say there's a weak breaking of the one form symmetry or something.
Right, exactly. That's I would be looking for something where you have a one form symmetry where the breaking of the one form symmetry goes as 1 over M or something like that. Because
yes,
I mean, I would think when N and M are very large, it's very hard for the physics to tell the difference between, you know, M equals 1 million and N
that is true. But at the end of this cascade, you will see the difference, right? Because here you will end up with SUM, but
right.
in other case, there's another step. You basically end up with SU1.
So you're saying in the infrared, these will look totally different because one will be confining, one's not.
Yes.
That's interesting. So somehow, even though these two theories look almost exactly the same, one of them's confining and one's
And
not.
you could maybe say something like the breaking of this one form symmetry is a very small effect, and you could try to do some perturbation in that. I haven't thought about this, but just from looking at it here, right, you would at the end of this not just end up with this pure null theory for SUM, but just with SU1, which is sort of a trivial theory.
Right, right. Now, that's why I was asking. It's because on the one hand, it looks like these things should be almost the same as if the one is not there, but on the other hand, they look very different. Okay, do we have other questions from the participants?
Yes, there's a question
Jakob
by
Moritz.
Jakob Moritz.
Yeah. Hi. Thanks for the nice talk. I wanted to follow up on Watty's question, and your answer to it, because I would have thought that so from the supergravity solution, I can change your capital N just by changing the UV cutoff. So that just since the radial scale corresponds to energy scale and N varies logarithmically, I can just go from N equals to Km to N to
This
K
is
plus
what
1.
you are talking about, right? That
Yeah,
there's
exactly.
R0 and you can change the UV scale.
Right, exactly.
But then what happens is only at these values will you really have sort of a dual interpretation. Right. So I think there are two aspects to this. It's an interesting question. Maybe there's something one needs to think about it more, but certainly only for these values of K, RK, you actually do get sort of an integral number of branes, and then you have some potential dual description. But also at the end of this flow, right, you end up only, but you have to then glue in, the second point is you have to glue in this T star S3 solution, right? Far in the UV, you can totally stick with the T11 and you'll be totally right, just a conical solution. But then as you go to the IR, you actually need to put in the T star S3. And I think at that point, you need to sort of make sure what exactly, is there now really still remnant symmetry left over?
Yeah, so my interpretation would have been that if you sit in the IR at the bottom of the throat, then there's a tiny it's very hard to detect N from N to distinguish N from N plus 1, because it has to do with, let's say we couple it to a compact bulk, and it has to do with how long the throat is towards the UV, which is a UV question. But yeah,
I'm not coupling it to a compact bulk, right? But I think so. Indeed, if you're coupling it to a compact bulk, maybe there's some story you can run with it here. This is literally, there should be a field theory dual, and in this case, the field theory dual would be something like SU1, right? If in this case, you would at the end of the cascade is the SU1 theory.
But if you don't couple it to a bulk, then for N, I mean
okay,
N is not
I don't know
well
what you mean
defined,
with bulk, but there is a bulk which is, of course, the supergravity solution. So there's this M5, there's a radial direction, and there's R4. It's just that the bulk for me is not anything that's compact, it's just R4.
Okay, thanks. I'll think about that.
So Fabio has a comment, maybe you want to unmute yourself and make the comment. Alternatively, one can work in terms of page charges. The flux point is going to depend on R, yes.
Okay. All right, great. Well, thanks very much. Let's thank Sakura again, and actually thank all the morning speakers for the first session. And Jim or Fabian, do you have something you wanted to add before the coffee break?